All right, this is lesson 27, example problem 1B. So if you haven't watched the 1A video, please go watch the 1A video first. There are some numbers we're going to use from 1A and not calculate in this one because they've stayed the same from problem to problem. So from 1A to 1B, we took what was our rectangular cross-section B, a rectangular cross section for our beam, and cut it up and made an I-beam shape. All right, so we're given that the distance of this middle section is 10 inches and the flange is 5 inches in width. It also tells us that each of these guys is 1 inch in thickness. 1 inch. Okay, so a couple things that can stay the same. So the maximum moment did not change for this problem. If you were to go through and solve for the reaction forces, those stayed the same. Therefore, the shear diagram stayed the same. Therefore, the moment diagram stayed the same. Therefore, the maximum moment is still going to be 937,500 inch-pounds. So that's going to significantly shorten this problem. All right, so it asks us to calculate the new maximum bending stress and determine if the beam will fail. Right, so bending stress is equal to the maximum moment. That should be M subscript max. M max times C over IX. So we have the maximum bending moment. That's already done. So C is the largest distance from the centroid x-axis to the end of the beam. So if we draw the x-axis going through the centroid of our beam, that's right there. And then so the furthest distance away would be either all the way up at the top or all the way down at the bottom. So if the whole distance in the middle of the beam is 10 inches, that means that this distance is 5 inches. Therefore, this distance is 6 inches. So that tells us that C is equal to 6 inches. So then the last thing we need is the moment of inertia in the x direction. So there's no way to get out of this one. We're going to have to actually go through and calculate the moment of inertia. So same way we've done these beam problems, I'm going to break it up into an A, a B, and a C. So for A, Ix bar is base height cubed over 12. So that's going to be 1 inch times 10 inches cubed over 12. So that's going to be 83.3 inches to the fourth. Then we decide if we have to use the parallel axis theorem, right? So if we look, the centroid of shape A is on the x-axis for the center of our entire I-beam. Therefore, the parallel axis theorem isn't required. Our D is 0, so Ix is equal to Ix bar is equal to 83.3 inches to the fourth. All right, so if we do shape B, Ix bar B is equal to base height cubed over 12. So the base for B is 5 inches. The height is 1 inch cubed over 12. So if we go ahead and plug all that in, 5 over 12 is 0.416 inches to the fourth. Then if we look for the parallel axis theorem, X bar B plus AD squared. Right, so the centroid of B is all the way up here. That is not at the same as the center of our beam. So this distance is going to be 5.5 inches. So that's our D. So we're going to have 0.416 inches to the fourth plus area for a rectangle is base times height. So 5 inches, 1 inch, and then our D squared. So for IXB, that'll give us 151.7 inches to the fourth. Okay, so then if we look at C, Shape C is the same as shape B, so IXC is equal to IXB is equal to 151.7 inches to the fourth. So if we want to do the entire shape IX, that's our IXA plus IXB plus IXC. So that's our 83.3 inches to the fourth plus 151.7 inches to the fourth plus another 151.7 inches to the fourth. So we get that the moment of inertia in the x direction is 386.67 inches to the fourth, right? So just to compare, the moment of inertia for 1A was 166.67 inches to the fourth, right? So just by taking what was our rectangular beam and kind of cutting it up, right, and putting those pieces on the end to make an I-beam shape, we've doubled our moment of inertia. A little more than doubled. So let's see what that does to the bending stress now. So now we have bending stress is equal to maximum moment times C over IX. Our maximum moment was 937,500 inch-pounds. Our C was 6 inches. Notice as well that from part A to part B, our C got a little bit larger. So then divided by 386.67 inches to the fourth, we get that our maximum bending stress now is 14,547 psi. And if we look, it tells us that this red oak beam will break at 16,000 psi. 16,000 is greater than 14,547 psi. Therefore, the beam will not break, right? So we use the exact same amount of wood for our beam in between 1A and 1B, but by changing the shape from that rectangle shape to that I-beam shape, we've almost halved the bending stress in the beam. If you look back at 1A, the bending stress, maximum bending stress was 28,125 psi, which was greater than the 16,000 psi that would break it. So just by rearranging the shape of our beam, we are able to take it from something that will break to something that will not break. All right, and that is how you get through this problem.